Let's talk about a very interesting principle in physics, which you might have already heard of, which is the Liouville Theorem. This theorem states that the density of points along the trajectory in the evolution of a system is a constant. Saying it like this, it may not make much sense, so let's break it down. The main concept to understand here is that of phase space. The phase space in physics is a concept that's used to describe the mechanical state of a system as it evolves over time. If you consider, for example, a system that has n degrees of freedom, then the phase space would be a 2n dimensional space that represents the evolution of the system and its state at any particular moment in time. For example, if a system has two generalized coordinates, x and y, for example, then you're going to have the momenta associated to each of those coordinates, px and py in this case. So the phase space would be 4-dimensional in this example. If the system has three generalized coordinates, then you're going to have a 6-dimensional space because you need to consider the three components of the momenta of each generalized coordinate, and so on and so forth. To illustrate this, let's consider the classical harmonic oscillator, which is a very common example studied in mechanics. A very good example of a harmonic oscillator is an oscillating mass on a spring. The Hamiltonian of this system is given by this equation that you can see somewhere over here. What you can notice is that the trajectory traced by P and Q as the system evolves is an ellipse. As you may notice, this is simply the equation of an ellipse if the Hamiltonian h is a constant. Using Hamilton's equations, we can show that the divergence of the phase space flow of this system is a constant over time. What this implies is that the trajectories described by P and Q are closed loops, and that the volume of the phase space is a constant as the system evolves over time. The statement of the Liouville theorem then, in the case of the mass spring system, is that the area of the ellipse described by each Hamiltonian of the system is a constant over the evolution of the system. If we change the Hamiltonian, then the size of the ellipse can increase or it can decrease, but it should remain constant, or better still, its area should remain constant over time. And this is simply an expression of the conservation of energy. Again, it's worth noting that this theorem only applies to conservative systems. If there is, for example, a damping force like frictional forces, then the loops in this case are not going to be closed and the theorem doesn't apply. Going much further, we can show that the Liouville theorem is much linked to Noether's theorem, which describes an intricate connection between the conservation laws in physics and the symmetries of a system. If this is something that interests you, let me know and we are going to talk about this in another video.